So in last lecture, I have discussed with you that uh, the aromatic electrophilic substitution reaction. And before that, why the name is aromatic, why the name is electrophilic, why the name is substitution reaction is given to that reaction specifically. For example, nitration reaction, sulfonation reaction, or halogenation reaction. So aromatic electrophilic substitution reaction is very important or easily given by the benzene molecule. Now, why aromatic electrophilic substitution reaction is possible on the benzene ring? It's very important. As you know that benzene has a pi electron cloud which is present at the above and as well as below side of the plane of the benzene molecule. Now, you can say in other words that this pi electron cloud is present at the above side as well as below side of the sigma bond framework. Just like a framework is there, and this framework is made up of sigma due to the sigma bond. Hence, benzene having a pi electron cloud, and hence benzene is favorable, benzene is susceptible for the electrophilic attack, and that's why benzene undergoes very fastly, very easily substitution reaction rather than the addition reaction, rather than the oxidation reaction, which is not possible on the benzene molecule. So this aromatic electrophilic substitution reaction involves a two-step mechanism, which I have explaining here with you. I am sharing with you these two steps in a detailed way. Just to observe each and every step, it will be helpful to you to clarify the exact mechanism of different aromatic electrophilic substitution reaction, maybe of nitration reaction, maybe of sulfonation reaction, maybe of that is halogenation reaction, or it might be Friedel-Crafts acylation reaction or Friedel-Crafts alkylation reaction. So students, I request to all that you should please keep your attention toward this one, how the systematic or stepwise mechanism is involved for the aromatic electrophilic substitution reaction. Just in step first, there are 6 sub-steps are there. How this step first is involve different 6 stages of mechanism. Just in step first, that is part 1a, I have represented on this slide. In first step, what happens, or step A, what happens, this electrophile is there having a positive charge and benzene acting as a good source of electron, and this benzene having a pi electron cloud at the upper side as well as lower side. Just earlier I have discussed with you in last lecture also. As electrophiles will becomes closer to this pi electron cloud, that is electrophile having a positively charged species, and this positively charged species or electrophile approaches to the benzene molecule, or you can call it as a approaches to the carbon atom of benzene molecule. And if this electrophile approach to this carbon atom of benzene molecule initially, now what happens, and this electrophile forms the partial bond. This is a weak bond, partial bond between this ring carbon and itself, that is electrophile. And this partial bond formation between ring carbon and electrophile is called as a transition state, and this transition state we can designate it as a transition state 1 or transition state first. Are you clear what happens in first step? In first step, electrophile approaches to the one carbon of a benzene molecule, and they are trying to form the initially partial bond is formed between ring carbon and electrophile, that is called as a transition state 1. Now what happens in this case? There are 6 electrons, 6 pi electrons, 2 plus 2 plus 2, 6 pi electrons are there, and out of these 6 pi electrons, 2 pi electrons, you may consider this bond, 2 pi electrons are utilized or used to form the bond between ring carbon and electrophile E means out of 6 pi electrons, 2 pi electrons are used, 2 pi electrons are utilized, 2 pi electrons are consumed to form the sigma bond between the ring carbon and electrophile. And if the two pi electrons are used to form the sigma bond between carbon and electrophile, this ring bears automatically positive charge. Now, this as this ring carbon becomes, or overall ring becomes positively charged. Initially, the benzene ring having 6 carbons, all the 6 carbons was sp2 hybridized, sp2 hybridized. But if electrophile attacks on the one of the carbon atom, on which carbon electrophile is attacked, that carbon becomes sp3 hybridized. Now sp2 hybridized carbon, if electrophile is attacked on that carbon, it will become sp3 hybridized. Now how many? These 5 carbons are there. Out of 6, 1 carbon becomes sp3 hybridized, and remaining carbons remains as it is in the same hybridization state, that is sp2 hybridization state. Now, these 4 pi electrons, 2 pi electrons are utilized to form the bond between this ring carbon and electron. And remaining 4 pi electrons, they are continuously delocalized from one carbon to another carbon between, within the ring. Within the ring. That's delocalization. Here I am shown here. If this electrophile is attached on this one ring, this second carbon becomes positively charged, and now this 2 pi electrons or pi bond will be shifted here. Again positive charge is here. To neutralize this positive charge, this bond will be, yes, shifts here. Again there is a positive charge. So there is a involvement, there is a delocalization of positive charge from this carbon to this carbon to this carbon. I have shown here, these are the different resonating structure. This is 1, 2, 3. Now you may called as here, these 3 resonating structure can be written in the form of this shortly I am representing here the newly resonating hybrid structure, which have positive charge within the ring, and all these 5 carbons are sp2 hybridized, but this carbon is sp3 hybridized. Now as positive charge becoming more stable due to delocalization of this positive charge from one carbon to another carbon, this is a ion, or you can call it as a carbon having a positively charged ion. And this carbon positively charged ion is called as a arenium ion. In, you don't confuse with that, this arenium ion is also called as a sigma complex. In different reference book, this complex or this arenium ion is also called as Wieland intermediate. So these are the 3 names for this complex. One is arenium ion, another is the sigma complex, or you can call to this complex as a Wieland intermediate. Are you clear this? This arenium ion is get stabilized due to delocalization of this positive charge over the ring forming corresponding to the resonating structure. Means this positive charge will be well stabilized due to delocalization of this positive charge from one carbon to another carbon over the ring forming corresponding resonating structure. Now, as you have shown here all these steps or all these structures here, and lastly there is a formation of arenium ion or sigma complex. The formation of this arenium ion or sigma complex is a very slow step reaction. So any reaction which if the reaction or step is slow, then this step will be considered as a exactly rate determining step. Means we can easily calculate the order, we can easily calculate the speed of that reaction. So as the reaction is very slow, or you can call it a slow reaction, so it is called as a rate determining step. That is again I'm repeating, the formation of arenium ion or sigma complex or Wieland intermediate is a slow step, and that's why this step is known as a rate determining step of this reaction. Now I'm shifting to a second step. In the second step, how there is a formation of different transition states are there, and lastly on elimination of one proton, the all carbon, how it becomes sp2 hybridized with electrophile. Now friends, just you see here, bonding between carbon and hydrogen is also here. Hydrogen is already, one of the hydrogen is already there from same, that is benzene molecule is there. As ring carbon and electrophile becomes stronger bond, or they form the strong bond between ring carbon and electrophile, or this bond, as this bond becomes strong and strong, at the same instance the bond between this carbon and hydrogen becoming weak. Now the bond becoming weak means there is a partial bonding between the ring carbon and hydrogen. Now the ring carbon and hydrogen becomes partially weak bonding is there. That's why I have shown here this hydrogen becomes partially positive, because this hydrogen shows here weak bonding between sp3 hybridized carbon and itself hydrogen. That's why this step is called as the transition state second, TS second I have shown here. Now, in next step, what happens? This is called as rhenium complex, rhenium ion, or Wheeland complex, or sigma complex. Now, this rhenium ion loses this proton, because this proton and ring carbon becomes weak bond, weak sigma bond is there, and that's why this proton will be loses rhenium ion. This entire rhenium ion loses this proton from the carbon atom, which bears electrophilic nature, electrophile here. Now, benzene again regains two electrons means four electrons were already there, four pi electrons are already there, and these two pi electrons, or these two electrons becoming a part of aromatic 6 state, and that's why again 6 electrons will be regains here, and that's why this step, last step, is elimination of proton, or losing of proton is there. And if proton is loses from this transition state second, automatically only electrophile will be attached to this benzene molecule with the elimination of H plus. Now here all the carbons are now again, or you can call it as a regained sp2 hybridized. Here initially if electrophile attacks on this carbon was sp3 hybridized, but now if elimination of proton is there in the transition state second, all the carbons becomes sp2 hybridized with elimination of proton. So in this step second, what happens? The loss of proton takes place very rapidly. That's why I have shown here this step is very fast step relative to the step first. Step first was slow. That's why rate determining step. So this step is very fast. So there is a no rate determining step takes place during the formation of transition state second, or during that final elimination of the proton. So hence this step is fast step and has no effect on the overall rate of the reaction. So if you check the energy profile diagram, how the sequence of the mechanism takes place, I have shown here by the plot of energy versus reaction coordinate. So this graph of energy versus reaction coordinate called as the energy profile diagram. Just friends, show here, I am showing here, just you observe here, this is the benzene molecule. When electrophiles comes closer to benzene molecule, the energy will be automatically increases. It increases to maximum, that is called as the transition state, and this step is called as what? In the step first, I have shown with you that how the transition state 1 was there, and the difference between the energy from this position to this position is called as the energy of activation, that is 1. It is the maximum amount of energy required to convert reactant molecule into transition state. That maximum amount of energy is called as the energy of activation. So this energy of activation is called as the EA1, because this that is aromatic electrophilic substitution reaction involves two steps. So that's why two energy of activations are there. So in first step, this energy of activation is there. So this energy of activation is required for the conversion of reactant into transition state first. So again, if transition state first is formed, now again there is a decrease in the energy, and this is called as a complete formation of transition state 1. And in the next step, as there is a elimination of proton, I have just shown with you regarding this step first, step second, the elimination of proton is there. This step is fast reaction. I have also shown here in the energy profile diagram. So this step is fast. Again, there is a slight increase in the energy, and again there is a formation of a transition state. So this transition states second I have shown here, and if you check the distance between this one and this one, this is called as the energy of activation second, this distance, or EA second. This reaction is fast. Again, there is a rapid decrease in the energy, and there is a stable energy is there. So as you are observing that reactant molecule is here and the product molecule is here. If you compare the energy of reactant molecule and product molecule, the product molecule having lesser energy, and that's why this energy profile diagram suggests us that aromatic electrophilic substitution reaction is exothermic reaction. Exothermic reaction, because heat is evolved during the formation of this electrophile substitution, and that's why the energy of the product is less than the energy of the reactant. So this reaction is exothermic reaction. So just to check the energy profile diagram for the aromatic electrophilic substitution reaction, it tells us more how the energy of activation 1 takes place, how the energy of activation 2 takes place, and how the step 1 is slow and second step is fast, and how the product and reactants having the different energies, and it suggests that the reaction is exothermic with us. Now, friend, just to observe, I have just discussed with you that how aromatic electrophilic substitution reaction takes place. Some of the examples I will discuss with you regarding this aromatic electrophilic substitution reaction. Now, one of the reaction which is mentioned in your syllabus is nitration reaction. Nitration. The word nitration means nitric acid is used, sulfuric acid is used. That reaction is called as a nitration reaction. Now, what happens in the nitration reaction when benzene is heated in the presence of a mixture of concentrated nitric acid and concentrated sulfuric acid at 50 to 60 degrees centigrade? What will be the product? The product will be nitrobenzene. Again, I'm repeating, when benzene is heated at 50 to 60 degrees centigrade with a mixture of concentrated nitric acid and concentrated sulfuric acid, the product is nitrobenzene. Now, why we are using nitrobenzene? Sorry, why we are using sulfuric acid? Because during the formation of nitrobenzene, only NO2 is used, or NO2 is generated from the nitric acid. Why we are using sulfuric acid? The role of the sulfuric acid is here is concentrated sulfuric acid, which increases the rate of reaction by increasing the concentration of electrophile, that is nitronium ion. If we add sulfuric acid with nitric acid, the electrophilicity of nitronium ion will be increased due to the presence of sulfuric acid. And that's why we are adding sulfuric acid with concentrated nitric acid here. The sulfuric acid acting here as to increase the rate of reaction by increasing the concentration of nitronium ion, which nitronium ion generated from this nitric acid. And that's why we are using sulfuric acid. Friend, just you see the common reaction I have represented here. When benzene molecule reacted with nitric acid and sulfuric acid at 50 to 60 degrees centigrade, there is a formation of a nitrobenzene. I have shown here the structure of nitrobenzene. So, how mechanism takes place during the formation of that nitrobenzene? So, in step first, what happens? We are using here nitric acid as well as sulfuric acid. H2SO4, I have shown here H2SO4 in different fashion. H2SO3 and 1. This is H2SO4. You don't confuse with this structure of H2SO4. I have shown in another way H2SO4. And this is a nitric acid, HNO3. This is NOOO 3 times. So HNO3. This is nitric acid. I have shown here this nitric acid also in a different way, in another way. So this is sulfuric acid and this is a structure for nitric acid. Okay. So this nitric acid accepts proton from the sulfuric acid. This nitric acid pools, accepts this proton from the sulfuric acid. I have shown here one of the proton of the sulfuric acid by pink color, one of the proton of the nitric acid by red color. This pink colored proton is attracted toward this nitric acid. Now nitric acid will have how many protons? 2 protons are there. This pink colored protons comes from this sulfuric acid. So this red colored proton was earlier present on this nitric acid. So nitric acid becoming the structure like this. So here OHH, as oxygen become trivalent, 1, 2, 3 valencies are there. So oxygen bears positive charge. Again, already nitrogen having positive charge. As the oxygen bears positive charge on its one, dehydration takes place. In second step, what happens? This protonated nitric acid dissociates to form the nitronium ion. So just to check here, this OHH means H2O is there. This water molecule will be, yes, removed from this uh, complex of nitric acid and sulfuric acid. What happens? Only there is a material, remaining structure is NOO, that is NO2, just NOO, that is called as a nitronium ion. Already nitrogen having positive charge is here. This is a nitronium ion. I have shown here also positive charge. Nitrogen with two oxygens and NO2 with positive charge. This NO2 positive you can call it as a nitronium ion. Friends, you check it, check or observe it carefully, that how this nitronium ion as acting as a electrophile is generated during these two steps. In first step, sulfuric acid donates proton to nitric acid and formation of a complex. In second step, nitric acid complex eliminates water molecule and formation of a nitronium ion. And this nitronium ion acting as a electrophile to attack on the benzene molecule. See here in the step third, what happens in step third? In step third, nitronium ion, which is generated in step second, NO2 positive ion, which will be attacks on this benzene molecule, and this step is slow, and as the step is slow, this is the rate determining step. Again, there is a formation of a transition state 1, and this carbon is sp3 hybridized, remaining carbon remains as it is, sp2 hybridized. As earlier, the common reaction, I have common mechanism in the aromatic electrophilic substitution reaction. I have shown here how the delocalization of pi bonds from one position to another position, and how the positive charge shifts from one carbon to another carbon and gets stability. These three are the rhenium ion, or you can call it as William complex, will be formed. And lastly, these three can be denoted by one structure, that is resonance hybrid structure of rhenium ion, or resonance hybrid structure of this intermediate. You can call it as a rhenium ion of this nitrobenzene or sigma complex or William complex. So now, if we shift to step 4, in the last step or step 4, there is a elimination of proton from this rhenium ion, which is abstracted by the base HSO4, which is prepared in step second, and there is a formation of a nitrobenzene. Just to check here, this is a Wieland complex or rhenium ion reacted with HSO4. Uh, to whom this HSO4 comes? This HSO4 comes from step 1. So this HSO4 acting as a base, this base attacks on this hydrogen, which eliminates the proton from this sp3 hybridized carbon atom of benzene ring, and formation of a H2SO4. Are you clear here? H2SO4. Now, as there is a elimination of proton or removal of proton from this benzene carbon, all the carbon becomes sp2 hybridized, and the positive charge will be stabilized by formation of a sigma electrons during the aromatic 6 state. And that's why benzene becomes stable by forming a 6 pi electron cloud, and by the elimination of proton, NO2 will be strongly attached with this benzene carbon or ring carbon, and formation of a nitrobenzene. So nitration reaction involves 4 steps. In step first, sulfuric acid donates proton to the nitric acid. In second step, nitric acid complex eliminates water molecule and generation of a nitronium ion. In third step, generated nitronium ion attacks on the benzene molecule. There is a formation of a transition state 1, and this transition state 1 forms different resonating structures, and these different resonating structures you may called as a rhenium ion structures or sigma complex or Wieland intermediate. This rhenium ion sigma complex or Wieland intermediate in last step eliminates proton, and this abstraction of a proton will be takes place by the attack of HSO4, which acting as a base, and this HSO4 is prepared in step first, and this HSO4 attacks on the protons of the benzene ring carbon, and thus aromatic transition state second will be formed. And this transition state second, after abstraction of a proton, the benzene gets highly stable, and that's why nitrobenzene is formed as a final product with elimination of sulfuric acid. Or if you put water molecule here instead of HSO4, you may use water molecule here. which might be acting as a base for the elimination of this proton, for the abstraction of this proton, and the product will be H3O positive. So in this case, step fourth is a very fast step. This is not a rate determining step, sorry, or you can call it as a, this step is not used for the rate determining step, but transition state first, or step 3, that is attack of nitronium ion on benzene molecule. This process or this step is very slow, and that's why this process is used to determine the rate constant or rate. So this step is called as a rate determining step. Just we see next reaction from your syllabus is halogenation reaction. Friends, you know the word halogenation means what? Uh, any reaction which is carried out in the presence of halogen is called as a halogenation reaction. Now, halogenation reaction may be carried out by different ways. In different ways means what? In different ways means halogenation reaction may be carried out on electrophilic sorry, on aromatic ring, or aromatic halogenation reaction may be carried out on the aliphatic compounds also. As we are generally discussing here about the aromatic electrophilic substitution, this halogenation reaction takes place on the aromatic ring, specifically here on the benzene molecule. So benzene reacts with chlorine, bromine, or iodine, or the fluorine. That reactions are called as a halogenation reaction. Now here I am going to discuss detail about the halogenation reaction. When benzene reacted with chlorine or bromine, just I have shown here, I am shown here benzene reacted with chlorine or bromine. Now which is the catalyst, which will be best catalyst for this halogenation reaction? The catalyst is Lewis acids. What are the Lewis acids? For example, I have reported few Lewis acid like ferric chloride, ferric bromide, aluminum chloride. These three are the best catalysts for the halogenation reaction of benzene. So it produces the product chlorobenzene or bromobenzene. If you use chlorine, the product will be chlorobenzene. If you use bromine, the product will be bromobenzene. When again I am explaining same. When benzene reacted with chlorine or bromine in the presence of Lewis acid like ferric chloride or ferric bromide, and you may use aluminum chloride, it produces the product chlorobenzene. If you use chlorine, it produces the product bromobenzene if you use bromine respectively. So I have shown here, when benzene reacted with chlorine at 50 to 60 degrees centigrade, ferric chloride is the catalyst, that is Lewis acid. Then there is a formation of a chlorobenzene as a main product with elimination of hydrochloric acid. Now, if you want to carry out the bromination of benzene molecule, it will be easily possible by using benzene with bromine, molecular bromine at 50 to 60 degrees centigrade. The Lewis acid, which are acting as a catalyst here, ferric bromide, and the product is bromobenzene, and the byproduct is hydrobromic acid or HBr. Now, friends, just you see here how the mechanism takes place regarding this halogenation reaction. Either the reaction may be bromination or may be chlorination. What about iodination and fluorination? I will discuss in next slide. But before going to start that iodination or fluorination, I want to discuss with you the detailed mechanism of bromination reaction of benzene. Just step 1, step 2, and these are the 3 steps I have shown here on this slide. It represents us that how bromine will be attacked on the benzene molecule and formation of a bromobenzene. So now here, this is a step first. In step first, there is activation of Lewis acid. This is a ferric bromide, FeBr3. This ferric bromide reacts with molecular bromine for the activation of Lewis acid. Now there is a formation of a complex. Ferric bromide complex is formed. Just to check, only this Br2 will be attached to that ferric bromide, FeBr3. Now this is called as a complex. During this complex, these two bromine atom, this is the first bromine atom, another bromine atom is there. This bromine atom gets positively charged, partial positive charge is developed on this Br and negative charge on this Br. Now this is the complex. Now this complex is highly unstable. Now what happens? As the complex is unstable here, this Br negative eliminates from this one, or Br negative comes from this complex, and this Br negative will be came in contact with benzene molecule only this Br negative came in contact with benzene molecule. Now just I have shown here this Br, and this is a hydrogen, and the positive charge is there. So this step is rate determining step, or very slow step is this one. Br will be attached here with positive charge, and Br is here, and this uh, reaction, or the sorry intermediate, is called as the arenaeum ion or sigma complex or Wieland intermediate, with elimination of FeBr4, but this FeBr4 having a negative charge. Now in step third, earlier I have discussed with you that step third in the aromatic electrophilic substitution is abstraction of proton. In this case also, these 4 pi electrons are there. These pi electrons are entirely delocalized from one carbon to another carbon, but one of the carbon is sp3 hybridized carbon. To get stability to this entire benzene molecule, one hydrogen should be eliminated from this one. So this hydrogen will be abstracted, eliminated by this FeBr4 molecule, which acting as a base here, and this reaction is very fast. So this proton is eliminated by FeBr4, and formation of a FeBr3 plus HBr as the byproduct, and bromobenzene is the major product which is formed during the process of bromination of benzene. So again I am repeating here the detailed mechanism of bromination of benzene. In first step there is activation of Lewis acid, or you can call it as a formation of a complex between ferric bromide and molecular bromine. In step second, this formed complex generates bromonium ion which attacks on the benzene molecule, and this is the rate determining step or slow step, and formation of a arenaeum ion or sigma complex, which having Br is one of the main substituent. And in last step, that is deprotonation step, one of the proton is removed from the benzene molecule which containing bromine atom, and this HBr is eliminated with FeBr3 as a byproduct, and final product or major product is bromobenzene in this case also. So these are the 3 steps in which the bromination reaction takes place. First step, activation of Lewis acid, or you can call it as a complex formation with Lewis acid. Second step, attack of Br positive on the benzene molecule and formation of a arenaeum ion. In the third step, abstraction of proton, or you can call it as the deprotonation reaction, and finally formation of a bromobenzene. Now again, if we move to next reaction, that is iodination. Iodination reaction is not possible on the benzene molecule. Why iodination reactions are not possible on benzene molecule? Because iodine is very unreactive, not suitable or not good electrophile to attack on the benzene molecule. So if we carry on the iodination reaction with benzene, iodine molecule is unreactive. Now if you react this iodine, what happens? The reaction is highly reversible. Instead of loss of proton, there is a loss of iodine. In previous case, just to observe here friends, in the previous case I have shown here what in step third there is a deprotonation. So actually for getting the stability to this entire benzene molecule, the proton should be eliminated from this one. Instead of elimination of proton, what happens in the iodination? Iodine is eliminated, so iodine will be here, so iodine is eliminated, and that's why iodination reaction is not possible on the benzene molecule. There are 2 reasons for the iodination reaction, failure of the iodination reaction. One reason, or first reason, is iodine is less reactive or unreactive. Another, if iodination reaction undergoes benzene on the benzene, the reaction is reversible. Instead of loss of hydrogen, there is a loss of iodine. So if there is a loss of iodine, there is a no substitution reaction, and that's why iodination of benzene is not possible in easy way. If we use oxidizing agent, strong oxidizing agent like nitric acid or iodic acid, you can use you can perform the iodination of benzene by using oxidizing agent. Not only oxidizing agent, you can use strong oxidizing agent here. Then iodination is possible on the benzene molecule. So what about the fluorination of benzene molecule? Fluorination of benzene molecule or fluorination reaction of benzene is a very vigorous reaction. Vigorous reaction. Heat is evolved during the formation or during the fluorination reaction. So this reaction is vigorous, hence direct fluorination